Hi, I'm Eric Lindsay, and I am a disabled veteran, paralyzed from the C5, C6 vertebrae as a result of a freak bicycle accident. I came to QL Plus and the UTSA engineering department with a problem. I would like to be able to plug in my electrical devices. I have very poor finger dexterity, and as a result, I am unable to grab power cords and plug them into devices or walls. And so I presented this problem statement and challenge, and am hoping for a cool solution.
The Helping Hands team was challenged to create an assistive device for the hand, and our goal was to create a high-quality, affordable orthosis that would enable Eric to grasp and plug in cables and cords. We strived to create a device that was adaptable, modular, and would fit in with Eric's lifestyle. The device should be able to actuate both mechanically and electronically. Using Eric's gross motor movement, we wanted to harness the natural coupling motion between wrist extension and finger flexion, known as tenodesis.
We developed an electro-mechanical orthosis, or ELMO for short. The ELMO consists of two major components, a hand orthosis responsible for engaging the hand, and a forearm brace which houses electronics. The hand orthosis features a 4-bar linkage system, a ramp for the index and middle fingers, a loop for the thumb, supports for the palm, as well as a linear actuator.
The linear actuator transmits force directly into the device. Torque is applied throughout the linkage system and couples motion between the fingers and the thumb into a strong grasp. One linear motion from the actuator allows the hand to achieve the full range of grasping mechanics. The actuator extends and contracts to open and close the hand.
That is cool.
The forearm brace houses the device's electronics. This includes a 9-volt rechargeable battery, a PC board with a buck converter to adjust the voltage for the actuator and surface electrode. The surface electrode acts as a signal to activate the actuator. An Arduino Micro acts as the brains, and a rocker switch allows us for ease of operation. The ELMO is controlled by electromyography, or EMG, which is a concept introduced to us by our mentor at Alt-Bionics. The surface electrode measures latent voltage activity in the user's arm. A muscle contraction causes a spike in this voltage due to a release of ions in the tissue. The Arduino Micro captures and interprets this input signal, and an output signal is sent to the actuator based upon the desired relationship between muscle activity and activation of the motor, otherwise known as gesture control. Gesture control is achieved through the coding of the Arduino. As the electrode measures the latent voltage in muscle tissue, this also means that there is maximum voltage achievable through muscle activation. Threshold can be set between the relaxation and maximum contraction of the muscle to let the Arduino know when to activate the motor, or whether the intended muscle contraction was not to activate the ELMO.
The hand orthosis parts were 3D printed at the UTSA's makerspace. A durable resin was chosen as material for its stiff and pliable properties that make it ideal for cyclic loading and wearable devices. Additional parts were CNC machined in 6061 aluminum alloy. We began fabrication of the forearm piece by taking a cast mold of Eric's arm. This was done with help from InMotion Prosthetics. Brace fabrication continued via collaboration with Specialty Prosthetics and Orthotics of Texas, where the cast was poured, modified, pulled with plastic, and trimmed. The forearm brace consisted of 2 thermoplastic shells, a soft inner lining made of ethylene and a rigid outer shell made with carbon fiber and hardened with resin. Vacuum-formed hollows were created to fit electronics between the inner and outer shells.
We evaluated our device on parameters of weight, grip force, grasp speed, grasp configuration, and dexterity. The ELMO successfully imitates a 3-jaw chuck grasp. It also supports the cylindrical and tripod grasps, while providing at least 11 newtons of grip force for each. The time it takes for the device to close the hand into a grasp from rest position is 2 seconds. The device weighs 0.93 pounds, and most importantly, it is capable of grasping and inserting electrical cords.
In conclusion, the ELMO device met the specified design criteria. Our device is able to assist our intended user grasp and plug in cables, as well as assist him in other daily activities. Our hope for the ELMO is to improve the quality of life for our intended user, expand the capabilities of orthotics, and leverage this technology to support larger populations impacted by diminished hand functionality, such as persons with spinal cord injuries and Parkinson's disease. We believe that a helping hand has the power to change a life.
We would like to thank Eric and Suki Lindsay, Ryan Saavedra, Max Cruikshanks, and everyone from Alt-Bionics, Imelda Peña of InMotion Prosthetics, Ed Koo, Johnny O, Adrian, and Priscilla of Specialty Prosthetics and Orthosis of Texas, all the UTSA staff for their assistance and guidance, and everyone else that has helped support our team and our project.